Today, our webinar is on decarbonization, a roadmap for decarbonization for Indian cement industry, a topic which is very relevant today when we're talking about our environment and about climate change. This webinar will be presented by Mr. Dinesh Satija, who is Head of Process Department in Holtec. I would like to hand over the presentation to Mr. Satija now, who will be conducting the webinar today.
Thank you, Shalini. As we know that today's topic is decarbonization, and you must be hearing this word very frequently nowadays. So it is important to declutter because decarbonization is very widely used word, but it is important to declutter what is decarbonization. So we thought let us have a session on this. So I'll start my presentation on decarbonization. As we can see the process of basically, if we talk of decarbonization, essentially the process of CO2 emission, reducing CO2 emission from industrial, energy, and transport sector, where mainly the fossil fuel is used, and we involved to convert from fossil fuel to renewable or low carbon alternatives. So this also include technological shift, process improvements to limit carbon output. And if we see to just get an overview, we are given a global CO2 emission status. Currently, we can see its total global emission 2024 data is around 41.6 billion tons of. This is an estimate. And if we see the highest emission is coming from China, 30%, US 15, EU 9, and India 8. So India also has a great role in emission, but definitely China, US are on the upper side, and remaining with Japan, Russia, and other countries. Now, why do we need decarbonization? The first thing which I think we are experiencing in our daily life is combating climate change. We are finding it extreme weather situations, either it's raining very heavily or extreme winter or extreme summer across the world. It's not in one country phenomenon, it's across the world. So it is important to reduce greenhouse gases to slow global warming. Then protect public health. This will involve lowering of pollution, improving air and respiratory health. So it is ultimately protect for decarbonization is having an important role in public health protection. And then another important aspect is ensuring energy security. The moment we decarbonize, we are forced to go towards from fossil fuel to renewable energy. And renewable energy has to be indigenously produced. It could be solar, it could be wind, or even other small forms of energy. So it substitutes fossil fuel and it increases the energy security for a country. Just to give you a perspective, India is having around 9 to 10% of the oil they are keeping as a reserve, just to take care of all these wars and any eventuality in the abnormal situation, which they want that we have to be secured. They want to go for another 30 days. So basically, because of all these wars, everybody wants to have secure their energy. So it will be a great if we can convert into renewable energy, which will be an indigenous product and reduce our dependence. Similarly, when we convert to renewable energy, it encourages green jobs, green shift to green technologies, and there will be another new investment, new job creation. So it will also boost the economic growth. Now, what is our national commitment as a country? India is committed for net zero emission by 2070. That was finalized that was declared or pledged in COP26 in Glasgow on November 1, 2021. The main commitment regarding climate are expanding non-fossil energy capacity to 500 gigawatt by 2030. And India will meet 50% of the total energy requirement using renewable source by 2030. And you must have heard in the news recently, currently we are already at 50%. Our energy requirement is coming from renewable energy sources. We will reduce our projected carbon emission by 1 billion tons by 2030. The baseline is 1.56 billion, 56 billion ton in 2005. Just to give you an idea, this this figure of 1.56 in 2005 is projected to go up to 4.48 gigaton. So India will, that if business as usual, it will go to 4.48. But India is committed to reduce it by 1 billion tons. So the ultimate target is to remain within 3.48 gigaton at 2030. Similarly, another parameter is that reduce carbon intensity, that is CO2 emission per unit of GDP. So India is committed for 45% reduction by 2030. Baseline figure is 425 tons CO2 per million GDP on purchase power parity basis in data of 2005. And just to give you an idea where we stand, current value for this is against 425, we are at 373. And the world average is, global average is around 386. So we are at close to the global average. So this gives an idea that we are on the right path, or at least we are moving the right direction and very fast. Now we'll come to the cement. That was Indian target is for the whole industry, every complete as a country whole. We are focusing on now cement. So what are the major source of CO2 from industry? Cement industry is basically there are two sources. One is direct, another is indirect. Direct sources include raw material calcination. We know, being in cement industry, that limestone, once calcined, they emit CO2. So that is one of the major source, which contribute about 56 to 60%. And another source is fuel, because in India is a coal-based cement industry. So coal-fired fossil fuel is a major source. We are where it comes around 30 to 35% CO2 through that, and rest indirect is use of electricity and transportation, which contributes about 10 to 12% in the overall scenario. Now we have to decarbonize. So what are the various levers which need to be pressed for our journey for decarbonization or net zero by 2070? First is clinker efficiency, thermal, then alternate fuels, use of supplementary cementitious material, decarbonization of electricity, then new age binders which are coming, which will be coming more and more in future, then recarbonation, cement use efficiency, rather using cement efficiently, and then the final is mother of all is carbon capture, utilization, and storage. Now, Indian cement industry decarbonization target. If we divide our targets in two parts, one targets are set for 2030, another is for 2050. Emission intensity will be reduced by 35 to 40%, and in 2050 it will be 50 to 60%. Then blended cement ratio 75% plus by 2030, and 2050 shift to net zero cement. So it will be majorly blended cement. TSR, if we talk 25 to 30% by 2030 and more than 50% by 50. Renewable energy uses more than 30%. And in 2050, we foresee widespread use of green hydrogen, alternate fuel, biomass, no fossil fuel. Waste heat recovery more than 60% in 30 and more than 90% by 2050. 90% of the potential. Carbon capture and storage, as per the projection, is by 2030 we could see pilot projects initiated. By 2050, we'll see that pilot projects are converting into commercial production and bigger size units. So we can foresee that coming years, maybe after 5, 10 years, we'll find that carbon capture is also realizing it's on the ground in India also. Now we go for the decarbonization roadmap. This is with respect to Indian cement industry. If we are currently at an average of say 680 based on 2020 basis kg CO2 cement, and our target is to go 2070 at net zero. So what are the various potential areas and how much potential is there? That is depicted in this chart. So about 2 to 3% in thermal and electrical energy reduction we could achieve. AF fuel switch, alternate fuel, biomass, etc., 21 to 24%. Then clinker factor reduction, use of converting to blended cement, LC3, etc., 18 to 25%, WHR 4 to 9%, and then renewable energies uh, will be around 4.5 to 7.5% potential. Transportation converting to EV vehicles or hydrogen, green hydrogen shift for transportation, 1.5 to 3%, and new age binders recarbonation around 1.3 to 1.5 to 3%, and carbon offset by changing investment policies, new project funding, that also gives a boost to 3 to 7%. And whatever left out finally will be have to be done through carbon capture, which may be around 19 to 45%, whatever is left out of all other efforts. Now, clinker efficiency, if we talk, the goal is to reduce thermal energy from 731, that is a 2020 average country basis, to 731. Gradually, it will go to 705. And 705 also takes care into consideration the increase in energy consumption due to deployment of CCUS. Because by the 2070, most of the plants will be running with CCUS. So that also has a power consumption. So once that also is adjusted, so final goal is for 705. So this particular case will have a 1 to 2% saving with respect to thermal energy. Alternate fuels. The target mix for 2070 is 50% green hydrogen, 35% waste derived fuels, and 15% biomass. So you can see the shift from 95% fossil fuel to almost zero by 2070. And green hydrogen will be the player for the next, right, from 2040 to 2070, rather 2035 to 2070, from 10% in 2047 to 50% by 2070. So this will be the fuels for future. And challenges are definitely supply chain, segregation, and pre-processing. So these challenges will be faced, and then solution will also come once challenges are there. Solutions also will be explored. And CO2 potential is around 21 to 24% in this. Now, next important lever is supplementary cementitious material. So basically our aim is to reduce the clinker consumption, clinker proportion. So currently 2020, if we take an average of industry average of 0.75, this is targeted for 2070 as 0.56. So that will have that will essentially use slag, fly ash, calcined clay, limestone, increase in proportion of that, and increase in proportion of blended cement to 90%, and reduction of clinker factor from 0.75 to 0.6. So this has a CO2 reduction potential of over 18 to 25%. So if you see the chart for supplementary materials, blended cement, we'll see the OPC is going down, even PPC is gradually going down, and then PLC is increasing. Similarly, composite cement is increasing. LC3 will be increasing very fast in the coming years. Now we talk of decarbonization of electricity. as we know, the current industry, power generation is through coal only, majorly. So that also is another area where decarbonization will be required. So when we talk of power consumption per se, our target is from 73 to 65 per ton, and increase in waste heat recovery capacity. The current capacity is around 530, 538 megawatt, which has a potential up to 1100, even up to 1300 is also projected. So that has to be that remaining gap has to be covered. Then shifting to green electricity with renewable energy. As we said, we are moving very fast with respect to renewable energy, and the CO2 reduction potential with these measures, with all these three, works out to around 9.5 to 18.5%. The new binders, which are currently not much in use, the still development stage, but we can see in another 10, 20, 30 years, these will be very important in reducing CO2. Like LC3, it has a potential of 40%. Calcium sulfoaluminate, that is another type of cement binder, which uses mainly bauxite, limestone, clay, and some other material, but reduces only limestone use is only 40%. But and then temperature, burning temperature is around 1200. So it has a potential to reduce CO2 emission. Use of geopolymer is again a very important development which we'll see in the future. 80% potential. Then magnesium-based cements, 100%. Then carbonated table cement. So these are the under developing stage. One reason which are not coming up fully is because the cost of productions are high. But with the scale increase in scale, the cost of also will be workable in future. This is what is expected. But CO2 potential is around 0.1 to 1%. Now, if we come to cement use efficiency, so currently, if you see concrete usage, 22 to 20 basis, 65% of cement is used, concrete is used in structural application, and 29% is via MCC and RMC, and 36% mixed on site, which is a very crude way. So it is important that mostly it should be converted to RMC. And even RMC functioning quality control also needs to be improved to get the exact design of the concrete should be made without any excess cement or any other issues. Similarly, use of plasticizer to lower water cement ratios. Then correct size of the aggregates is very important. And in this, we are likely to see advanced practices like precast and pre-engineered building component, which will be manufactured in an environment which is totally controlled and accurate. Use of ASC blocks instead of clay bricks, replacing mortar with adhesive, then construction demolition, waste recycle that will be used in the construction. And then another advanced technology will be coming is the 3D concrete printing. That will be a very accurate concrete design and very precisely constructed. Then automated concrete design system and optimization of structural geometry. So these are the things which are likely to see in future. That also has a scope for CO2 reduction because cement use will be very optimized, accurate. Now we come to the carbon capture, utilization, and storage. Uh, Basically, if we talk of carbon capture, it is essentially the separating CO2 from flue gases of point source. It could be chimney stack of a cement plant, steel plant, iron, or a power plant. So CO2 will be separated from the chimney, transported into a storage or a utilization site, and depositing it, or it can be either deposited deep into the seabed, or it can be utilized. So that it should not escape. Basically, we have to, whatever is captured, it has to be utilized industrially, or it has to be buried in the earth. It could many times it is buried in the depleted oil wells deep into the sea. Reduction potential here is 19 to 45%. Then there are many CO2 capture options. What we will be talking, which is more relevant to CO2 capture, is a post combustion method that involves removal of CO2 from after fossil fuel has been burned. Once we see in our chimney, we can see about CO2 emission is around CO2 is around 18 to 22% CO2 from the cement plant chimney. So if we attack on that, that is after the fuel is burnt, CO2 is finalized, then we will capture CO2 from there, which is, and this method is basically, it's most useful, most suitable for cement plant because fundamental changes required will not be much. So one technology which we discuss here, there are many other technologies which we are not taking currently. We are taking one technology which is amine scrubbing technology. So the basic material which is used for scrubbing is monoethanol amine is a primary amine solvent, and it is used in the post-combustion CO2 capture due to its high reactivity. It is highly reactive. It has high affinity with CO2. So this process is commercially matured and its relative is simplified in plant integration with cement plant. The integration is easy. So this is finding more, acceptability with cement industry. So typical process is chemical absorption, amine based, and status is most matured post-combustion CO2 capture technology. The key performance metrics is CO2 capture efficiency could be around 85 to 95, and CO2 purity is 95 to 99%. It is again energy intensive, 3.5 to 4 gigajoule per ton of CO2 capture. That is the energy requirement in this. We will just give you a brief about what is the process exactly, just an idea. So what we can see, the cement plant, we get flue gases, which is being, which will be pre-treated. We know CO2 is normally say 18 to 22%, but typically it also uh, has a NOx, SOx, dust and water vapors. So all these NOx, SOx, water vapor and dust, they can create problem with use of MEA. So this has to be removed first. So all these gases are removed, our temperature is reduced from up to 30, 40 degree, and they are scrubbed. SOx, NOx, even dust is filtered from there. So what we are going ahead with the gases which are having CO2, of course, but no SOx, NOx, and dust. So that will go to the absorption column. We call it absorber. So that will be, MEA will be flowing downward and CO2 gas will be moving upward. The gas rich with CO2 will be moving upward. So there will be an absorption taking place. So we can see the lean gas will pass from the top, that will be water washed so that no MEA is carried away and no other pollutants are going away. So we get lean gas out of the system through stack, and the the MEA which is rich in CO2, now it will be further treated. It will be pumped to, and it will be preheated and it will be sent to stripper, you call it desorber column. There it will be heated to 120, 1 to 30 degree, and from there it CO2, it will release the CO2 and lean MEA is recovered back and it is pushed back into the system, and CO2 separated from there is compressed. That will have 95 to 99% purity, and it will be either pumped through pipeline or storage or any other tanker or whatever means for further use. So this is a simple process. Process is not simple, but I have explained in a very simplistic way. Process is complex. So now we have a curiosity. What is the status of CCU in India. So current status in India is no large scale implementation yet. A few Indian cement companies are exploring pilot at this stage. Barriers are, of course, high cost, lack of infrastructure, and need of policy funding support. These are the major barriers. So currently, we are not even at pilot stage, or at the most, we may be coming in coming years. We will see if some pilots are operational in some of few of the plants, which is again our target for 2030. Now, global and what are the global and Indian initiatives are? There are some GCCA and global CCS institutes are studying for CO2 hubs, storage and financing. And Niti Aayog has recommended for development of CCUS cluster because CO2 can be, there could be a cement cluster where CO2 is captured by many plants. In future, I'm talking. And then it has to be, there has to be some common infrastructure where that shared infrastructure CO2 will be transported, maybe further use or any other use that will be shifted from that location to some other place where it can be processed for further use. Different uses will come in the subsequent slides. What could be other uses? Challenges are, as we told earlier, capex is very high currently. Other challenge will be transport and storage. Infrastructure require pipelines, storage sites are generally, if we have to store or we have to, we need depleted oil fields, or we have to take it to the user's site. And we need additional power for CO2 separation. So these are broad things. So we are, you can say we are only at the pilot stage, not even executed pilot project. But maybe coming years, we can see, we will see some development in this direction. As I said, it's expensive. So just to give you a perspective, though there is no, in India, we have not seen anything, but for a capture of 1 million ton CO2, which can be captured through a 4,000 TPD plant, if we take an estimate of capex, it could be as high as 450 million USD. And OPEX could be as high as $25 per ton of CO2. These figures looks abnormally high. Just to give you an idea that how the price falls over a period when economy of scale works. We know around, we can now see the solar power plants. If we see the price of solar power in 2010, it was 17 rupees per unit. And in last 10 years, the solar power scale has gone very high. Currently, we are producing 50% of our requirement is met through solar, wind power, renewables. And you know the current price of solar power is 2 rupees. So you can imagine from 17 rupees, it has come down to 2 rupees, another 10 to 15 years time, just because the scale has gone very high. So we also foresee that in future, when the scales go up, the capex, OPEX, everything will come down drastically. So our next thing comes is what is the utility for CO2 capture? What we should do after capturing? So if you see this matrix, there are vast uses. The CO2 use is not new. Already industry is using. Only thing is what we will be giving, CO2 will be captured and green CO2 can say. So if you can see it can be used in food product, fuel recovery, plastic, fire suppression, inverting agent with some miscellaneous use as a refrigerator, dry ice. We commonly see all these in fisheries, in ice cream business. People commonly see dry use of dry ice. Then there are chemical uses also can be used in cement, chemical industry, extractant, mineralization. So like there is a vast number of usage. So what we are talking mainly now in chemicals is basically converting the CO2 to methanol, urea, PO, carbon monoxide, or methane. And from there, methanol, we can convert this into liquid fuels, fertilizer or secondary chemical. So what we will be focusing in our remaining slide, next slide will be on liquid fuel. Because once cost is very high, CO2 capture is high, so we must think of using CO2 for some very high value products so that it becomes viable. So liquid fuel can be a very good option for high value product. So this can be used for production of sustainable aviation fuel, which we call it jet fuel. One is conventional jet fuel, which comes from fossil fuel. What we will be talking is sustainable aviation fuel, SAF, which is coming from captured CO2, which can call it green fuel. So SAF is an alternate jet fuel made from non-petroleum feedstock, has similar chemical and physical properties as conventional fuel, which has got very significantly lower carbon footprint. It reduced emissions. It can reduce emission by 80%. Drop in fuel. This can be used as blending with the conventional aviation fuel, even up to 50%. And some trials have also been made by adding 10-15% in the STF conventional aviation fuel, and it was successful. So unlike conventional fuel, crude oil, SAF comes from a variety of sustainable sources, which CO2 capture from cement industry could be one source. This is a simple block diagram because we are talking of sustainable fuel and carbon neutral. So beside carbon capture is our feedstock, we need renewable energy and green hydrogen for that, which will be CO2 will be converted into methanol. Methanol will be converted into, you can say, crude aviation fuel, and then it will be processed further to make it final version of sustained aviation fuel. So this process is possible very much, and we could see in future this kind of fuel is coming. It could be used mixed form. It will have a lower footprint, so it will be in demand for an hour because aviation industry again has to go carbon neutral. So this will be an important material for them, and it will have a high value. Just to get a global perspective with respect to India, EU, China, USA, if we talk of average clinker factor, it is around 70 India, 75 EU, China 65 to 75, USA 75 to 80. AFR use around 5 to 10% India, which is quite low in catching up now. EU is 40 to 70, China is 10 to 20, US is 20 to 25%. WHR adoption has picked up in last many years. 50% plants are now having WHR, 90% in EU, 80% China, and 70% USA. CCUS progress, if you talk, in India, we can only say 20, the pilot stage will be coming in coming years. And EU, some of the CCS are in operational stage, initial operational. And China, again, it's an early stages. US, again, in the scale up from pilot to commercial. One important factor is carbon pricing. That makes the project, improve the project viability. In India, still nothing is there, though this kind of trading will be coming in future. We are still in the formation stage only. EU, there are operational, but prices are also, look, there may be very variable prices, but typically 75 to $80 per ton. China, again, it's a very initial stage, no firm policy. USA is less than EU, maybe around $25 per ton. So if we talk of decarbonization initiatives in Indian cement industry, we will take two groups in this. Just installed capacity 60 million, 184. Renewable energy 300 plus megawatt, wind plus solar, another 150 megawatt. Then 40% total energy from renewable, and then 25%. So we can see renewable energy has gone up. Their target for 50%, and in another case, it will be significantly increased. Energy intensity reduction is 10% and 7% in other case. CO2 emission intensity is 12% and 5%. So this is the current situation with the two groups, which are, so it looks that most of the plants are now pushing for decarbonization with a significant speed. If we talk of leading projects and partnership, we can see that NTPC Green and Honeywell has signed and I have an understanding to develop SAF from NTPC power plant will capture CO2 and will be SAF will be produced, and green hydrogen plants also will be installed in Vizag. IOCL and L&T Energy Green Tech have come to an agreement. They will be putting 10,000 TPA green hydrogen plant in Panipat Refinery, Haryana. PPCL and Semcop joint venture by large green hydrogen production portfolio. AM Green Gremco 4,500 megawatt RE from CIL Coal India Limited to produce green ammonia hydrogen. GAIL is going for 10 megawatt electrolyzer for green hydrogen. Oil India Limited 99% pure green hydrogen pilot for fuel cell application. And we know Adani New and Industry Limited, they are coming up with a huge complex in their Mundra, at their Mundra complex. It will be a 1 million tons per annum green hydrogen, which can be scaled up to 3 million tons. Regarding sustain SAF pilot and developers, Honeywell again and NTPC, they are exploring e-fining based SAF and cement power from cement and power sector. Exitel India pilot plant especially, they are developing for SAF units. So Indian Oil, BPCL, HPCL, research and development in SAF technology. So as basically we are advancing towards production of green hydrogen, then renewable energy, which will ultimately will be used for production of sustained aviation fuel. So we are at either pilot Z or concept stage, or it's very initial stages. Now, if we talk of Holtec's role in decarbonization, we have been carrying out studies. It could be energy and process audits for reduction of specific heat consumption, specific power consumption, and process debottlenecking for capacity enhancement, which can ultimately end up with fuel and power saving. Then clinker factor reduction, use of SCM, how to increase consumption, WHR integration, AFR integration, use of alternate fuel and raw material, grinding optimization, reduction of power consumption in cement grinding, either directly or by increasing production. Then energy efficient design. Even for greenfield project, our effort is to have the most efficient design right from the concept stage. The execution also involved complete. We have set up for basic engineering, procurement, detail engineering, equipment inspection, site supervision, etc.